All right, everyone. I want to make a little video since today's pi day. So as you might remember what pi is, well, if we have a circle and maybe make it a little bit bigger and its radius is 1, well, you might remember the area of the circle is pi r squared, and in this case, our radius is 1. So our area, the size of the circle, is just pi. So how do we find out what pi is? How big is the circle of radius 1? Well, Archimedes had this idea of using regular polygons, so like squares, hexagons, pentagons, dodecagons, to approximate the area. So if we put a square on the circle, the area of the square is bigger than the area of the circle, and we could just measure the size of the side length of the square, which is 2, which is the size of the diameter, and area of the square is just side length squared, so it's 4, and this shows that pi is less than 4, which we hopefully all knew. And we could put a square inside of the circle, and the area of this inner square will be less than pi, and just do a little bit of geometry to find the side length of this square, and we can see that the side length is square root of 2. So the area of the inner square is 2. So pi is between 2 and 4. All right, and that's just using a square. Archimedes used other shapes, so if we drew a hexagon, maybe not so regular in this picture, but if we still have a radius of 1, we could do a little bit trickier geometry. And we know that the angle has to be, well, 2 pi over 6, which is, or the angle is pi over 6 in this case. The angle of the bigger triangle going from this corner down here to here would be 2 pi over 6, and this is half of that. So just some basic geometry shows that the length of half of the leg of this hexagon is 1 over square root of 3. And so once we have that size, we could get the area of the triangle drawn is 1 over 2 square root of 3. And if we multiply that by 12, we get that the area is, slight typo, it should be 2 square root of 3. So 2 square root of 3 is bigger than pi. And so Archimedes used this idea using a 96 gon. So imagine instead of just 6 sides, we had 96 sides. It would pretty much look like the circle. And using a smaller and bigger one, you got bounds for pi, this being the lower bound, 223 over 71, and 22/7, which you might have seen in grade school, was the upper bound. And just to give you an idea of the size of these, so 223 over 71 is about 3.14085, and 22/7 is about 3.1428, which, comparing that to 3.14159 for pi, you can see these bounds are pretty good, probably as good as they needed back in these ancient times. So those are the approximations we have using polygons. And you could do better, of course, but modern day techniques are much more accurate, and they'll get to trillions of digits of pi. So that's one thing I want to talk about. Another cool thing about pi is, well, if you remember from calculus, geometric series, or this is actually just from algebra, but we'll use this to do some Taylor series calculations. So 1 over 1 minus x, some basic algebra, shows that it's 1 plus x squared plus x cubed, and so on and so forth. This holds for all values of x. Its magnitude is less than 1. And you could check this, of course, if you plugged in like 1/2, it would be, well, 1 plus 1/2 plus 1/4 plus 1/8, and so on and so forth, would give you 2. And if we take this and we plug in negative x squared for x, we get a new Taylor series for 1 over 1 plus x squared, which is 1 minus x squared plus x to the 4th minus x to the 6th, all these even powers of x. And it's an alternating sum. And so that's another pretty well-known Taylor series. And if you integrate both sides, well, 1 over 1 plus x squared is the derivative of arctan. So integrating and then plugging in x equals 0 would give us the constant term is 0. So we get arctan of x as power series, which is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on and so forth. So all these tricks come from algebra and calculus. Where does pi come into play? Well, if we plug in x equals 1, then arctan of 1 is the angle that such that pi, sine and cosine are the same. So if x is 1, arctangent of 1, well, sine and cosine are the same when when the angle is pi over 4. So the left side of this equation would be pi over 4, and the right side would give us 1 minus the 3rd plus the 5th minus the 7th, and so on and so forth. So this gives us another cool identity for pi. Pi is equal to, well, 4 minus a little bit, so 4 minus 4/3 plus a little bit, 4/5 minus 4/7, and so on. Now, this isn't really the most effective way to calculate pi, but I thought it's a fun little trick, so I thought I'd share. So, really interesting facts about pi. So we know it's not rational. Maybe you remember that from grade school. So rational numbers are either terminate, if we're writing them in base 10, they either terminate or they repeat themselves the way 1/3 does or 1/7 does. Now, irrational numbers are plentiful and we could construct them. So those are the digits of pi, but this number here, 0.01001001, 4 zeros, and then there should be maybe a 5th zero, 6 zeros, 7 zeros, and so on and so forth. It's a irrational number because, well, it's non-repeating and it doesn't terminate. So it's not as interesting as pi in the sense, like, there's some pretty predictable patterns here of where we'll get 1s and 0s. Pi has shown a lot of different, statistically, that the numbers appearing in it seems to be random. So there's a concept that mathematicians have to describe this. It's called normal numbers. And so the idea of a normal number is that if you take any string of numbers, they each will show up the same amount of times in the decimal expansion. So, for example, if we look at 6, so the idea is 6 should appear about once every 10 times. So these are 50 digits and we have 3 6s, and The idea is the further and further you look down, 6 will appear once every 10 times. And that should hold for 7 and 2 and 8 as well. But this should hold for every string. So if you look at 89, then 89 should appear once every 100 numbers on average. So the really cool thing about this is if you pick any string, say a phone number or someone's social security number, the idea is if pi is normal, then even though you have a string of numbers that are really long, the probability of it occurring is positive. And the further down you go into the decimal expansion, you'll eventually find it. So whatever string of numbers, say everyone's age and height and weight and social security numbers, if pi is normal, will appear not just once in the digits of pi, but infinitely many times. It's pretty fascinating. And the thing is, we can't say this with certainty because we haven't proven that pi is normal. So this is still an open question. Mathematicians don't know the answer to it. So enjoy your Pi Day, some fun things to think about, and I'll see you next time. Make sure to click like, and comment if you have anything interesting to share, and subscribe.